Hi everyone, welcome to my video series. In this lecture video, I'll talk about the introduction to light. So I'll talk about what light is, and then we'll talk about one of the characteristics of light, which is the frequency of light, which refers to the color. But I'm going to go beyond that and talk a little bit about how we perceive color and why we see what we see. For example, when two types of light mix, they may make something that, might be a little different than what we were taught in, grade school or elementary school. So I'm going to talk about that too. So here we go. Chose a colorful background. I hope you like it. So this is really an introduction to light. So I'll talk about the properties of light, specifically relating it back to the wave characteristics and how light, how wave characteristics affect the qualities of light. So I'm going to go talk about that in great detail. And like I said, one of the biggest properties of light is the frequency, which is the color, and I'll talk about how we see colors as well. So in our course specifically, we actually will only deal with a little bit of the wave model of physics. Light is actually quite complicated, and in fact, it really needs its own course. In fact, you can take your own course in light and just focus on one of these two things called quantum mechanics or optics, so either way. But we're just going to focus on what is called the wave mechanics or the optics of light. So light can behave as a wave, and there's experiments that actually prove that it exists as a wave. One of the things is the Huygens principle and the Young's double slit experiment. But then there are other experiments to show that light actually acts like a particle, in other words, a physical matter that can actually push and interact with each other, which we model as photons, so little balls of light. Turns out they're actually both at once, and we made up a new theory called photon and the quantum model to kind of adjust for that. So we are not going to do any quantum modeling at all, but just know that there is a big model of light. So we'll start with the basic definition of light. Light is ultimately a electromagnetic wave. So let me get a prop. Oh, we'll use my lipstick today. So all light is a charge. It's usually a electron, but doesn't have to be. It just has to be a charge. And the charge has to go up and down like this. In fact, if you just spare me a quick second, let me open up something here. You know what I'm probably going to open up. My good old PhET program. But I actually like this because I think it really shows what light is in this kind of way. So let me go ahead and get that simulation. Play with sims. Come on, simulations. Usually it's a little easier to do this. Where are the rest of the simulations? Okay. Yes, we got it. Simulations. Here we go. Physics. I want the new ones. I want the old ones. Light. Okay. So where is it? Radiating charge. Okay. Sorry for the delay in this, but I find that this is actually very, very helpful for this. So what you have here is actually a charge. And when you have this charge kind of sitting in space like this, it makes what is called an electric field. So that's what these lines kind of make right here, right? So we didn't learn this in Physics 101 specifically, but if I taught in another class, I'm referring to the electric field. So what happens is a charge alters the field around it so that when other charges come close to it, it interacts very much like gravity, except instead of mass, it uses charge. Anyway, the point is, watch what happens when I give it a quick little shake. If I bump it, it's called. Let's give it a bump. There we go. Ooh, you can see that. Do you see that little wave? Cool, huh? So it turns out that a linear charge, so notice if I just move it like this, I don't make any waves at all. If you're moving at a constant velocity, we don't make or change that electric field in that way that I showed you earlier. But then I did because I stopped at constant acceleration. So in order to make an electromagnetic wave, you actually have to move it back and forth. Now, the only thing about this linear part here is that when it's moving like this, you actually make a magnetic field that's happening too. But usually the magnetic field is very weak compared to the electric field that is created. So let's go to my point though. Watch if I start to wiggle it, right? So you can even just look at this program right now and say, oh yeah, you're making a wave, right? Well, I'm basically waving around my electric field. Now, when my charge is stationary, I make that electric field. But as I start to move the charge, I make a magnetic field. So we get an oscillation of both electric field and magnetic field. So what happens is, if I make it go faster or slower, you can see I get some changes here. So light is part of the electromagnetic spectrum. So notice that I can change the frequency, right? And you get more wiggles. And more wiggles. And you can see it go like that. But there's no really set place where, you know, if I set the frequency to a very specific, you know, place that it's like, oh, it's definitely a microwave. So that's why we call it a spectrum. So it's not necessarily, you know, in one spot. But this is like, for example, the radio wave kind of looks like, well, let me give it a little frequency. It's a very slow moving, well, not slow, but it's a very small wave. Or actually, sorry, it's a very large wave. So this is like a radio wave. This would be like a microwave. Then the infrared wave. And then the light wave. And then the UV wave. And then the X-ray, and then like the gamma ray. So notice that what I'm doing is by changing the frequency, I change, of course, how many, you know, and this is the extreme case, right? Okay, probably losing your mind now. I'll give it a rest. But anyway, if you notice, by changing that frequency, I'm setting different parts of the electromagnetic spectrum. So frequency for light, it's about here, right? It's about in the a little more than the middle, actually, if I do it correctly. It should be more about here, like that. So that's an electromagnetic wave. Some of the other characteristics is that it's a transverse wave. So in other words, that the propagation of the wave is perpendicular to the disturbance of the wave. You don't need a medium for this. So that's the reason why we have light coming to us from the sun, which is hundreds of billions of miles away. We don't need a medium for that to happen. That's pretty important for, you know, our survival. So if we change the amplitude of this wave, what we do is we change the intensity. So another way to talk about intensity is in terms of light is brightness. So this would be if you had a dimmer switch and you put it up, the light would get brighter, and if you put it down, the light would get dimmer. You're changing the amplitude of the wave. Now, if you change the frequency, you actually change the color of the wave, and I'll talk about that in a little more detail as we go through. And another really interesting thing is that the speed of this is constant. In fact, all electromagnetic waves have the same speed. And the reason kind of why is the way that when you do this, when you oscillate a charge, this is setting the speed. Not so much the motion of this is not what I'm saying. I'm saying the charge itself is giving off the wave, and the wave that it gives off comes out at the speed of this amount. This is the fundamental property of light, and you know, Einstein's one of the contributors to studying this phenomenon. Actually, what his more famous recollection of the speed of light is that it is in fact constant no matter where you are. And that actually changes the way time works, which is why he's kind of famous. Actually, he got special relativity and Brownian motion, and he did a lot of stuff. But anyway, moving on. So I talked a little bit about this, but like I said, when it comes down to light, it's basically a wiggling electron. So it's, like I said, it's a little more halfway. It's about right here. So you're wiggling a pretty substantial amount when you do this. And of course, you know, this would be ultraviolet, gamma, and X-rays are just loaded with lots of motion when you do that, and that is the most energetic. In fact, a quantum property is that the frequency sets the energy, not the amplitude. We won't get into that, but for now, I'm going to treat it that way, that this is the most energetic, the gamma rays versus the light rays. So the speed of light, in fact, since it's a wave, we can use the wave equation. So instead of the v for speed of light, notice that you can actually use the c here. So the speed of light is characterized by the frequency and the wavelength. So you can do all sorts of calculations regarding and using the speed of light. So why don't we do that actually? Sorry, I thought I had this set up. I do not, so we will set it up right now. But they're pretty straightforward, simple calculations, but always worth doing just for fun. So let me get my little computer program ready to go. And I do have it ready to go. Look at that, I have all of my lectures ready to go. This is the one I'm working on though. So 2 questions. What is the wavelength of the radio wave 95.7 and how long does it take to reach Quinnipiac? So what I did here is had a little fun. So first of all, when you listen to a radio station, turns out that this number refers to a frequency. But usually it's just 95.7, 101.3, 104.1, but it's actually technically in megahertz, which mega means to M, capital M, is a metric unit for mega, which is times 10 to the 6th, right? So, therefore, 95.7 megahertz is the same as writing it as in 1 megahertz. There's 1 times 10 to the 6th. So notice I'm doing a conversion into regular hertz, because this basically, the reason why is because we're in meters per second here, and we have to keep it meters per second. There's no mega here. So when I do that out, here's my calculator. 95.7 times 1e to the positive 6, my fault. I get 9.57. And then do some 1, 2, 3, 4, 5, 6, 7, 8. Let me just double check that. 1, 2, 3, 4, 5, 6. That's what I thought. 7. Oops, not to the 7th. Times 10 to the 7th. Hertz. All right, I was going to say the 8. That doesn't make sense. Okay, so now we can calculate the wavelength, and these problems are very empty because they assume you know this value already. So why don't we get some blank paper here. So part 1 looks like this. The speed of light, or any wave, in the electromagnetic spectrum is c. So that is our known number, just like g is 9.81. It's pretty fast. And I actually, of course, rounded this number. It's technically like 2.9978. Like that, but of course, this is just fine. So looking for the frequency, we're looking for the wavelength. We have the frequency, which we said was 9.57 times 10 to the 7th hertz times the wavelength. So solving for the wavelength, I divide both sides by 95.7 to the 7th. I'm doing that right now as we speak. The wavelength is 3.13 meters. So fun fact, if this were me, I'm roughly 1.5 meters. You can imagine me. I'm pretty sure if you don't know me. That's about twice as tall. So, 3 meters is about 9 feet tall. So, that's a big wave. What this means is the size of this wave is this big, basically. So basically, one of these humps of the wave is the size of me. So that's pretty big. So that, in fact, is the wavelength of a radio wave, or the specific radio wave. And then how long does it take the radio wave to reach Quinnipiac? So, of course, I did this. Of course, I Googled the actual mileage and then converted it into meters to find this out. Since it's the same speed, we're going to use c here, and then I have the distance. So let's see how long it takes. Here's the speed is equal to the distance. Of course, I just scrolled this down before I read the number. 9012.33. This is a real number, in case you were super curious. And then I'm going to divide 9012.33 divided by the speed of light. And I'm purposely going to not write it in scientific notation. So 1, 2, 3, 4, 5. Nope. sorry, that's a 3, if you're following me. 3,00411 seconds. So less than, I mean, obviously less than a second, like way less than a second. So that's pretty cool, right? So it means that there's like literally no time delay between, you know, a radio speaker that's talking on live on the radio station versus, you know, how long it takes to get to your ears and for you to listen to it. So it just gets there. It's like if they're in the room with you. So that's pretty crazy, right? That's really cool. But anyway, so that's how you can use the wave equation. Remember, I call this the wave equation. Well, it is the wave equation. Not I call it, but it is the wave equation. And this is our velocity equation, right? So you can use either one of these to solve any sort of time, distance, frequency, velocity questions. Now remember, anytime you're using the wave equation, you have to use the, you have to look for frequency, because that's going to tell you which equation to use since they look very similar. Okay. What can light do? Well, let me put my pen down because light can do a lot. Like literally. So I am going to talk about what light can do, but I'm literally not going to talk about everything because we just don't have that time. One of the things light can do is reflect. So you have the privilege, if you're in the Physics 101 lab, to actually study the law of reflection. Since you have lab, experience doing it, I'm not going to teach it here, but pretty much it says the angle in equals the angle out. It's pretty straightforward stuff. And hopefully your labs, you saw that. And one example where light can reflect perfectly is a mirror, but that's not the only place it reflects. It pretty much reflects off of everything. But there's different types of reflection called diffuse and specular, and what's responsible for seeing a perfect image is specular reflection versus diffuse reflection. There's your mini lesson on reflection. Light can actually go through things, right? So like windows transmit light. So fun fact about windows, you always think you can see out of a window, but that's not true. Actually, you're watching the light come from outside into your eyes. That's how windows work. So naturally, if it's dark outside, the window looks black because there's no light coming in. You can't see anything outside. And that's why, not that, you do this on purpose, but if it's dark outside but your neighbor's light is on, you could see inside their house because there's a light source, and everything else is dark. Not that we're spying on our neighbors, but if the light was left on, we'll say that nobody's in the house, you can see that because the light's coming into your eyes, and vice versa. If there's light already outside, it comes into our eyes. So that's how light works. So you can transmit light. Things can absorb light. You know that, especially on a summer day, right? If you go outside on your pavement, especially if it's dark pavement, you'll notice that, in fact, it is warm. Another interesting effect about absorption is water on pavement. So you ever notice that, like, it doesn't matter what color pavement you have, if you put water on it, the spot with the water on it is darker. That's because light is absorbed through the water before it gets to your eyes, so less light gets to your eyes, so it appears darker, right? Of course, everything's cool in physics. Okay, moving on. I told you light could do a lot. Light can actually diffract, which means it bends around corners. It's pretty cool. If you think of a water wave coming up to a little barrier, the water will actually spread out after. Or another cool example is hearing around corners, right? I can actually keep my door, well, I usually keep it open, and with the door open, I can hear my son in the kitchen, regardless of the fact that there's an obstacle and a wall in my way. It doesn't matter, it goes around the wall and I can hear it. So that's diffraction. Light does this too, but since light's very small, you only see it in very, very small instances. I can diffract light off a CD, for example, because there's lots of grooves in it. And I have diffraction grating. When we do, unfortunately we don't have it in the lab that we do the diffraction grating lab, but it's pretty cool because you can actually see light actually separate out and bend around things. It's fun. Refraction is one of the labs that we do. So refraction is the bending of light because it enters into a different media. So our eyes work like this, our glasses work this way. Those are some major examples, but the bending of light as it passes through another medium. And lastly, I talk a lot about light, right? Scattering, so light can hit something and bounce off. In fact, this is the major reason why our sky is blue. It's mostly because when a lot of light, we have to be, it depends on how the sun is angled and all that fun stuff, but when you have a lot of light, and we have a lot of nitrogen in our atmosphere, it bounces off of that, and the remnants of that color that bounces off, it becomes blue. So it's a scattering. And of course, the light can actually change depending on the angle at which the sun and the atmosphere kind of make, and that changes the color, but we're not going to get into that stuff. You can see how complicated it gets. But some really cool things here. I do want to talk about color, though. So, like I said, the color, the frequency of a light wave denotes the color. And these are, your pretty standard frequencies. In fact, it's too bad that we don't do that lab, because I really like that lab, because you do this. You actually figure out the colors of the rainbow by diffracting the light and measuring the wavelength. You can actually do it pretty simply using some emission tubes and a light source. So notice that you have red, green, yellow, red, orange, yellow, green, blue, and purple, right? But notice that we don't have other colors like mint green or brown, or technically no white. There's no white light. We'll talk about that in a moment, because that's kind of interesting. So it turns out that what is there and what we see actually are kind of a little different. So our eyes actually work with these things called rods and cones, and you might even heard this in psychology. I know I took psychology, and I remember this section, but the perception of light and color. Color comes from cones. Cones are little receptors in your eye that are sensitive to wavelengths. In fact, it's most sensitive to green, less sensitive to red and blue. I speculate, although it may not be true, is that we're sensitive to green because if you look around us, I think some of the most common colors are green. That's not always true, but that's my little theory there. And that's what we see. I mean, of course, other stuff comes into our eyes, infrared, and ultraviolet, which is, of course, harmful for us. More on that when we talk about radiation. But interpretation of color actually comes by two theories, and it depends on what you're mixing. Are you mixing light or are you mixing pigment? If you're mixing light, you have your different rules, right? Most of you are familiar with pigment. When they tell you in elementary school that you use yellow and blue, in this case it's cyan, you make green, and you know that that you can make red and excuse me. Sorry about that. If you mix red and yellow, you make orange, right? I'm doing this with my 4-year-old daughter. She's pretty well versed in our colors. But this is pigment theory, or I noticed that it does say something different. It says color subtraction. But if you take flashlights, it turns out you got a different thing. In fact, if you mix red, green, and blue flashlights, you make white. It's pretty like what? And I used to teach high school, and I used to actually do this as a demonstration, and it always blew my mind when I took those 3 colors and it did make white. Now, if they're not perfectly, how should I say, if you don't have exactly the same amount of green, red, and blue, you won't make white. For example, if I had a little more red than blue and green, I'd make a pink. Or if I had a little more green and red, I would make like a yellow. So it has to be perfect in order for it to match. But we call this color addition, and then we have color subtraction. So this is more about the absorbance of light, and this is about the reflection of light. And it's exactly what I just said there. So the primary colors of light are red, green, and blue. And this is the additive color theory of light. And like I said, this is how stage lights work. So flashlights, I said stage lights. But ultimately, this is how our eyes work. It works on light coming into our eyes, the reflected light. So just to give you a quick little perspective, these are the wavelengths of all those 3 colors, and these are the primary additive colors. Also, this is a, blanking on the actual word that I'm trying to go. These are absorption lines here, so kind of a little chemistry here, but we're not going to, don't worry about that. It just is why I printed it in such an interesting way. But more importantly, the symbols for red, green, and blue are RGB, as you might imagine. Now, what happens is that when you mix the primary colors, you get what we call the secondary colors. In fact, the secondary colors are the following. Magenta is red and blue. Yellow is surprisingly green and red. And cyan, a light blue, is green and blue. Isn't that so weird, right? Like cyan is, a light blue is mixed by a dark blue and a green. Like that always like I can kind of get like this one. Yellow just doesn't make sense to me, and this one. But notice that basically magenta light is all three colors except for green. So in other words, what this means is that when you see something like this magenta color, your eyes are getting a lot of red and blue intensity, but pretty much little to no green intensity, hence the word minus green. And then etc. So when you see yellow light, your green and red cones are very sensitive, but there's no blue. So your mind has now made a new color. So for, well, not for yellow, but magenta. So just to be super dramatic, let's go back here. Notice magenta is not part of our wavelengths here, right? Magenta is what we interpret in our mind when we have those two colors happening at once. So when we have blue and red together, our mind says, okay, here's your new color, and it's magenta. That pink. Pretty cool, huh? Okay. So another two important things is white light is when all three cones are being used. So that is, again, another color for human perception. So interesting, right? When you get all three colors, you see white. And white's not a real color, it's just our interpretation of those three happening at once. And black is when light waves don't activate any of those cones, and then we interpret it as black. So black is another interesting color because it's not a real color, right? So there's actually other wavelengths that are out there, but those are just not ones we're sensitive to. So technically all other wavelengths look like this, like gamma rays look black, radio waves look black, just because it doesn't activate our cones that are sensitive to those frequencies. So because you have a lab in this, I'm not going to go through it, but this lab I think is really awesome because what happens is to make all these different colors, you have to change the intensity levels. So maybe orange is a little bit of more red, so I would do yellow, so green and red, but maybe a little less green and more red. So the intensity also matters. So if you have a lot of red light coming at you, it's going to appear more red. If you have less red light coming at you, then it's actually going to appear more of a brown color. So that's really cool stuff. And this same thing, this just blows my mind. So you could either use a yellow stage light or take a red and green one and put them over each other, and you actually will have yellow light. Your eye doesn't know the difference between these two scenarios. Pretty wild. Pigments. So absorption of light. So it's a little different. If you've ever noticed that your printer ink, right, always came in magenta, yellow, and cyan. I never knew why. Turns out that's because if you take these three colors, you get the primary subtraction colors, you get the secondary colors, which is the red, green, and blue, which is the additive primary colors. And in fact, you mix them all together, as you know, well, maybe not as you know, but if you mix those are going to, of course, make more of a brownish black color. So, you know, just a little bit about printing, right? So it's pretty cool. I mean, this is how your printer works. But fun fact, your printer won't actually use the black if it doesn't have to. So if you have something in color, but everything else is like black, like if you write a paper and you have one color image, instead of switching over to the black here, cartridge, it's actually going to use magenta, cyan, and yellow instead because it can make black that way. So if you ever wonder why you're always out of these colors, when you're not really printing a lot of color, but maybe one thing of color, That's the reason why. And of course, these three images are put together to make something like this. So this is based on why you see a color, is because some things absorb that light and give off another. So for instance, let me see if I have something specifically. Sure. I don't know if, yeah, you can see that, sort of. So this we see as blue. Now the reason why we see this as blue. Now notice that this doesn't give off its own blue light. This is a pigment, not a light additive. This works differently. This works on the fact that this pen actually absorbs color and then reflects another. So blue is basically absorption of red and green. So this is absorbing red and green light and giving back blue, which is why I see it blue. This is white. This is white because what's happening is that all three colors are actually being reflected off. And then black, all three colors are being absorbed. It's actually, let's see, there we go. Trying to make it look black. So, you know, if you ever noticed in the summertime you wear light clothing, right? You usually wear like, not necessarily white, but you could. But if you wear white versus black, you'll notice that it gets hotter, right? It's because the light is being absorbed. And that energy has to go somewhere. It goes into thermal heating. It goes into heating it up. So it's like walking over the dark pavement versus the light pavement, right? You ever notice that your feet feel better on that lighter pavement? And then, of course, things can get complicated. I mean, I think these are pretty self-explanatory. If I take white light, so in other words, the fact that my light right now is white, and I put this on a white surface, it appears white. The same thing, the light is white here. Put a white light on this, there we go, it appears blue. So this is, again, another way of thinking about this. So a magenta surface absorbs green, but then gives out red and blue. And green is basically absorbs red and blue and gives out green. But interesting, right? So what if you did something different? So in all of these cases, I've been shining white light, just like regular old light. But what if I took a different color light? Well, magenta is a combination of red and blue. So in other words, here we go. Although this is, of course, I'll do it like this. I'll draw on this. So if I took a green flashlight, so remember this is the flashlight now, so if I could draw a flashlight. There you go, beautiful. This is switch. But this is green. This is green light, right? Cool, I just happen to have the right color green. So I have a green flashlight, right? Now, magenta is something that is both red and blue, right? In fact, let me take a quick step back here, and maybe this might make more sense. Magenta, like we said, is red plus blue. So notice what happens to the light, right? When the red comes in, when the red comes in, it kind of like hits the red. And because red is already there, it kind of goes back out. And same thing, when the blue comes in, it kind of hits the blue, and the blue goes back out. So what happens is that because I have red and blue together, that makes magenta. Then green gets absorbed. So notice that green goes in and kind of sits here and then like stays here. So that's what I mean by green being absorbed. So same thing here. What happens is green is right here. So once green comes in, it hits green and goes back out. But red and blue have like a slot here. And since it's open for them, they sit here and stay. Where green doesn't have a slot, so it gets bounced off. Hopefully that made a little sense. Because now, if you notice here, I have an empty slot for green to sit because red and blue are taken and the last one's green. So if green comes in and sits down here, magenta absorbs green, then no light will come out, which means this will be absorbed as black. So you can do this as an experiment. It's cool. I don't think you'll be able to do it in this setting, but if I did it in a classroom, took a green flashlight and shined it on my my magenta calculator, it will look black. It's a cool demo. Vice versa. Notice here, I have red and blue. So I have a green surface with two openings for red and blue. Ah yes, red says I could sit here, and ah yes, blue is here. So if they stay and they're absorbed, there we go. These are absorbed. And if nothing comes out, that's interpreted as black, like that. So, color subtraction is a little different, right? So we have green and blue light coming in. This thing absorbs blue. So it means it has a spot for blue to sit here. So it looks like it absorbs blue, so blue will sit here. So the appearance of this will be green, because green will come in. And technically this is like a cyan color, but remember this said it absorbs blue, so it's going to reflect out green, because green gets bounced off. Boing, like that. And I did it kind of algebraically, if that makes sense. The light in is these two colors. And if I take out one of those colors, so light in is G plus B, and we're absorbing, so we subtract it out. So basically these cancel and we're left over with green. So let me see. Okay, yeah. All right, hold on one second. Okay, so let's do a few. I highly recommend doing my favorite thing. I would make you do this in class, of course. So why don't you take a moment and try these out and see if you could figure out what it appears to be, right? Try it out. These are difficult. In other words, I don't know what the answer is, to be honest, until I actually think through them. So just by looking at it, you shouldn't be able to do it. So you have to sit down, you have to think about what each of them means and what happens. So I'll awkwardly pause so that you can take a second to pause the video and try them out, and then I'll do them. Okay, so I think you paused. Here's how I do it. Magenta. So if it's not a primary color, I make it into primary color. So magenta is really what, red and blue, right? So this is what I do. Change it up. So actually magenta, I have red and blue, right? Now this, by the way, this is just coincidence that absorbs blue. It's not always blue, okay? So we absorb blue. So blue sits in here, which means it's going to reflect out the leftovers, which is red. Now, of course, these are just there for placeholders. It doesn't mean there's three. So the answer is red. I could also do the addition way. So red plus blue minus blue. If I do that, the blues cancel and I'm left over with red. So it checks out. Red in. Simple enough. Absorbs blue. Well, there's no blue to be absorbed. So red doesn't absorb red. Notice it doesn't say red, which means red will just go back out. It's not going to sit and hang out. So interesting. Basically absorbs blue is yellow. So if you shine a red light on a yellow page, it will actually appear red. So let's see. Red minus blue. Basically, I mean, this doesn't do anything. Gives you red. So this is where it kind of doesn't work. Green is not involved in this, apparently. Okay, let's see. Blue absorbs blue. Haha, so that sits in there. I don't know how to make this different from what I did before. So if it absorbs blue, it stays. Which means if nothing, so there's no red to bounce off and there's no green to bounce off. So in fact, this becomes black. There's no color. Blue minus blue makes black. So that's how these color things kind of work. I think I have a few online for you to try out too, so you can have fun with that. You'll definitely have one of these or two on your next assessment, so just be prepared to try to figure these out and solve them out. Okay, I'm going to end with a very quick video. This is called Minute Physics. It's totally worth it. It's a minute, so I don't feel bad showing you this. But I like it because it talks about why there's no pink light, right? So, here we go. We'll skip the ad.
The rainbow corresponds to different wavelengths of visible light. Red, orange, yellow, green, blue, and violet. Where's pink in that list? It's not there.
Yeah. There you go. Like I said, quick little minute physics for you. But anyway, so that basically ends my lecture on light. As you can see, light does lots of things. I'm going to go on and actually talk a little bit about refraction of light and bending in my next video. But I'm definitely taking a very more medical, biological approach to it and talking more about the eye instead of going into lenses, although lenses are, of course, very important. And I'll talk about nearsightedness and farsightedness and how the refraction of light changes how you see. I'll also talk about lens aberrations. In other words, there's defects in lenses that we have to account for as well. And I'll talk about those in our next video. And just to summarize too, there are two types of color addition. There's color addition, which uses light, reflection, and then there's color subtraction, which uses pigments and absorption. And as you can see, the color theory can get kind of complicated, so I highly recommend that you practice those out. So I'll see you in the next video. Take care.